What would the game of life sound like? Here's a possibility. In this patch, I'm sonifying the game of life, or more specifically, the red cells in this game of life. I'm doing this by turning jitter textures into jitter matrices, techniques that turn jitter matrices into data, and techniques that turn that data into multi-channel signals. For this, I'm using some of the new objects that came with the relatively new updates to Max, with 8.3, I believe. Objects like mc.snowphasor, mc.updown, which make it really easy to generate particle-like sounds, which fits very well with the sonification of cellular automata, like the game of life. This can be used in many ways to create interesting soundscapes, maybe more musical ideas or more noise-based ideas, but as long as you have the data, you can create cool things. This is a relatively complicated algorithm, so let's see how this is possible. And here I am exactly where I was at the end of the previous video. We have our jit.gl.texture, jit.noise as the starting point and this feedback loop to drive the game of life. Now, if I want to sonify this, I have to think of this in a few steps, right? So in very broad strokes, I say what I want to do is, first of all, get the jit.gl.texture into a jit.matrix. Now, if you have not seen the previous video or you just want to get into the sonification, you can also use the jit.convey object, right? This is going to give you a jitter matrix. As a result, it's a very easy to use object, and if you're not worried about the GPU, you can simply do this. But I have a jit.gl texture and I need this to be a matrix so I can work with this on the CPU level. And then, again, in a very broad way, I need to get information relating to the cells. We can define this later. And last but not least, I of course have to sonify the data. Again, easy to say. Let's see how this is going to work exactly. And let's do these step by step. So first of all, I want to get my texture. I want to turn it into a matrix. And this is very easy to do. I just need to use jit.gl.async reads. And if you look at the help file, it will say that it uses pixel buffer objects, PBOs, to perform asynchronous reads of open something complicated. Doesn't matter what it exactly precisely does, but what I care about is the fact that I can send a texture to this object and it's going to send out a jitter matrix containing the contents of that texture without a big hit on my CPU. So not a lot of lag, not a lot of slowdown, and I can really convert jit.gl textures into jitter matrices with this way. So that was easy, but I have one little problem, and that is the fact that this is really fast. This is 60 frames per second. So I get 60 matrices ideally per second. And if I'm going to process this, if I'm going to analyze the data and sonify things, this might be a bit too fast. And to deal with this, what I'm going to do is I'm going to create another jitter matrix, so jit.matrix. Let's give this 4 planes because the matrix data coming out of jit.gl async read is in alpha RGB. Float 32 data type, the same dimensions, 50 by 50. I don't want to make this too big since I'm going to go into the individual cells and their data, but that might be an option if you want to explore the sonification of bigger games of lives, as they call it. And I'm going to give this the attribute of through 0. This is the important one. Now, if I send this matrix here, so it gets converted into float 32, because it has the through 0 attribute, right? It is not going to show anything, even though the matrix is loaded here and it has received a matrix. If a jitter matrix has the through 0 attribute, it will only send out its contents if it has received a bang. Right, so by doing this, I can control the speed of my matrix output. And this means that I can work with this data at a slower rate and really get into analyzing the contents of this matrix. So let's create a metro object, right? Metro 250, so 4 times per second. I just have to toggle this on and okay, so now I'm getting a slower version of this matrix. So we are already doing very good. I can say my first step is done. But okay, now what? So now I have to get the information relating to the cells, and what exactly do I want to get here? So I know that I actually have 3 game of lives or games of lives here, right? I have the red one, the blue one, and the green one working all together. And I want to take this apart and I want to work with each color channel separately, right? So I want to take apart the JIT matrix into its individual planes, right? I want to only look at the cells that are passing through. So this means that I only care about the movement in the new cell. So filter out the new cells on each iteration. Right, so I can really track the movement and I can sonify the movement of the cells, which is hopefully going to be interesting to listen to, or it's going to give some kind of sonic context to what is going on visually. And then I want to figure out 2 things, right? So figure out the density of new cells. So how many new cells do I have on each iteration? How many alive cells do I have on each iteration? And the possible coordinates. So what are the coordinates of these cells? Can I have a list containing the x and y coordinates of these new alive cells? So, and with this information, I can create some kind of sonification algorithm. Okay, so let's put this here and let's see how we can do this. So to take apart the jitter matrix into its individual planes, all I have to do is to use jit.unpack and as an argument, the plane count, which is 4 in our case. But of course, the first plane is not really relevant to what we are trying to do. So if I do this, there is nothing because that's the alpha channel. But the first output, as you can see, this is the red channel, this is the green channel, and this is the blue channel, and this is not a channel, but it's just dump out, so it's not going to give us anything. But this way, I can have 3 instances of my game of life, 1 for each channel. Okay, so we're already doing pretty good, I think, but I have to also filter out the new cells on each iteration, right? So I have to figure out how to compare each new matrix compared to its previous iteration, how many new cells are there. And we can use these simple operators, jitter operators to do this. And this might look a bit complicated if you're not familiar with it, but I'm going to create an object called jit.!equals to p. Right, so this is going to do an operation on 2 jitter matrices. And what does this mean, if you don't know what this means? The exclamation mark here is, well, it's the exclamation mark, and equals to means not equal. So if I'm comparing the first matrix with the second matrix, which cells are not equal, which cells are different, and the p at the end means pass. So pass the cells that are different. So each time I send a matrix to the first inlet, it's going to compare it to the second inlet, the matrix in the second inlet. And if the cell is different on each cell, if the cell is different in the second matrix compared to the second matrix, it is going to send out that same cell. And it's very easy, in fact, to compare the previous iteration and the current iteration. I'm just going to use T for trigger, and then I'm going to type L as the 2 arguments, meaning lists, in this case, the jitter matrices. So I'm sending out the jitter matrix twice on each iteration. And what I want to do is, so each time a new matrix is coming through this jit unpack, I want to take this list and I want to trigger this comparison. So I want to compare this to whatever is in this second inlet. And afterwards, I want to again take the same matrix that I've just used to compare, and I put that into the second inlet, the cold inlet, meaning now that is loaded up. And what this does is then if the next iteration happens, and if I get a new matrix here, first I'm going to compare this with whatever's in the second inlet, which is the previous iteration. And once that comparison is done, I load the new matrix into the second inlet. And if you look at this, if we compare these 2, for instance, you can see that only the movement, only the new cells are passing, which is going to be the information that we are going to sonify. So this is a very neat trick for figuring out the movement in a constant stream of jitter matrices. Okay, so we can say that this is done. Right, we have taken apart the jitter matrix into its individual planes. We have filtered out the new cells on each iteration. And now the actual tricky part, now the actual complicated part, how do we figure out the density of new cells and the possible coordinates? Right, so I need a way to look at each individual cell, or I need a way to iterate between each cell. Right, so I can use, for example, the object jit.iter, which is going to iterate this jitter matrix. right? If I create a message box, you can see it's sending a bunch of zeros, but in fact what it's doing is, I believe we have a 50 by 50 matrix. So there are, on each iteration, this sends out 2,500 bits of information. If I open my Max console and clear it, and if I use print, for instance, you can see it's sending out a bunch of data. And if I stop this and if I scroll through this print, the chances are we are eventually going to encounter the value 1. I think it's there. It's really difficult to see. There we go. So print 1, print 1. So these are the values of cells. So it's really iterating through each cell and reporting its value. So we can use this to keep track of how many live cells we have, or we can really look at the coordinates of these cells that is also sent out by the second outlet of jit.iter, and then we can try to keep these as a list. But also I want to, if I close this Max console, I also want to figure out the density of new cells, right? So how many cells are there here with the value of 1? And for this, I can use a different object, jit.3m, so min, mean, max. If I send a jitter matrix into jit.3m, it's going to tell me 3 things. So first of all, what is the lowest value in the cell? What is the cell with the lowest value? In this case, of course, it's 0. There are a bunch of black cells here, meaning it is a value of 0. The second one is going to tell me the mean. So if I added up all the cells, and then if I divided this value by the amount of cells that I have, what is the mean value? And in this case, it's 0.008. And the third one is max. So what is the cell with the maximum value? What is the cell with the highest value? And what is that value? Of course, in our case, it's 1, because in our game of life, it can only be 0 or 1. And I'm not very interested right now in the minimum and maximum values, but I can do a neat trick where I take the mean, which is all the cells added up, and then divide it by the amount of cells, and I can just multiply that by the amount of cells, so kind of taking back the last step, and this is going to give me the sum, all the cells added up. So I know I have 2,500 cells in total. So I multiply this for this incoming value with that, and I get nothing. Why do I get nothing? Because this is a floating point number, so I need that tiny dot at the end. There we go. So now I know that I have 20 cells in this case. If I restart this whole process by banging this, as you can see, we have the population of our red cells in our game of life. We can, of course, easily apply this to the other planes as well. So we have figured out the density of the new cells, and we can try to get the possible coordinates in a similar manner. Okay, so let's implement an algorithm. What do I need to do? So I know the first outlet is giving me the values of the cells. The second outlet is giving me the coordinates, and I know this is happening from right to left, right? Max is always from right to left. So the coordinates are going to be 2 values. So you can see it always gives me the final one because this is so fast. 49, 49 starts from 0, 0, 0, 1, 0, 2, 0, 3, and then when that loops over 1, 0, 1, 1, 1, 2, etc. until it reaches 49, 49. So let's unpack this data. Unpack 0, 0. And what I want to do on each iteration, I want to not save this value, but I want to hold it. I want to store it in my memory by using the int object's second inlet. So now this value is going into int, but it is not being sent out unless I send a bang to the first inlet for both of these guys, right? So what I can do is each time I put the coordinates in int, so in the memory, and then I check if the value of that cell is 1. So I can use cell 1. And if cell 1 receives a 1, it's going to send out a bang, so I can simply do this. I can then bang out the information contained in my int objects. And then all I have to do is to save these in a list, right? And I know that the ZL group object is going to do this. If I don't give ZL group any arguments, it's just going to add the incoming values to an imaginary list, and then it's going to send out that list when it receives a bang. I'm going to do 2 of these, one for the x and y and one for the y coordinates. It's getting a bit cramped in here, so I will also zoom out. This is a nice trick. I'm going to create a button, and I'm going to put the button all the way down here. So now I have some real estate in this area. I can do some cooler things. Okay, but now each alive cell gets its coordinate recorded in ZL group, but it's going to do this for a very, very long time, and it will wait until I send a bang to show me its contents, and then it's going to start over again. So I have to automate this as well. I have to say each time you're iterating a new jitter matrix, please start over. Please send out whatever is contained here, and then start collecting the coordinates once again. And this is where we are going to use the dump out, which if I put a message box here, you will see that it sends out the message done when it's done iterating through this jitter matrix. So I can simply say cell done, so select the done message, and when it's done, when the bang comes out, just also send it to ZL group. Which means now ZL group is simply sending out the X and the Y coordinates. Right, and ideally these will be of equal length because, you know, you don't really just have an X coordinate. These are always coming out together. But now I have one list with the X coordinate of the alive cells and one list with the Y coordinate of the alive cells. So I have figured out the density of the new cells and the possible coordinates. Oof, all right, that was a semi-complicated algorithm. So now before we do something with all of this information, let's consider what we can sonify. And for this, I want to examine one of the new objects, right? If you have, at the time of this video, this is a new object with the new Max 8.3 updates. And the object I'm talking about is, I believe, called mc.snowphasor, which controls a population of phasors. So it's a fairly complicated object. There's a lot of things. I can start the audio. And you can see if I increase the probability here, it's sending out a stream of phasors in a multi-channel signal. Probably in the future, I will make a video where I go more into detail about all the possibilities of this object. But right now, I want to look at a specific version of this. And that is the audio mode or the audio input mode, or mc.snowphasor with the attribute mode 3. Now, when I have mode 3, this object is going to send out a phasor ramp. So it's going to go from 0 to 1, and one of its multiple channels, when it receives a click, you can already see it's sending out something. So we can use this, right? So I can really iterate through all the cells that are available, or depending on the density, I can send out a certain amount of clicks here, which are going to be manipulated. This incoming phasor ramp, this phasor signal, maybe can read through a buffer at a certain point of a buffer, depending on the coordinates of these red cells, maybe something like that. So we can figure out how this exactly works, but that's what I want to do. I want to trigger a certain amount of clicks. I want to trigger these phasor ramps, and I want to read through a buffer, an audio buffer, using this information, which will result in the sonification of the game of life. Okay, so let's set up our elements, right? So I have my mc.snowphasor, I have my attribute mode 3. And I think I also need the ramp time, right? So this phasor, how long in milliseconds, I believe, will it take for this ramp to happen? And let's just give it 200 milliseconds. Right, and I can also turn on my audio context by clicking Easy Deck, turning this on, and now let's see if I can visualize this in a way. So mc.meter is going to visualize this MC signal. Of course, I need to tell the mc.snowphasor how many channels it will have. Let's give it, I don't know, 200 channels. So at chance 200. So now this MC signal has 200 instances. Yes, you can see that's a lot. So if I do the same thing, if I have click tilde object connected to mc.snowphasor and I send a bang here, each time I'm getting a different ramp. This is not making any sound because this is just a value that goes from 0 to 1. All right, so how do we make sound out of this? So let's create an audio buffer, shall we? So I'm going to create a new object, buffer tilde. Let's call this buffer red because this is the red channel we are sonifying. And which sounds should we use? Well, I'm going to leave it empty for now. So this is an empty buffer, right? And I can, if I have an empty buffer, I can always drag an audio file. So how about some beatbox? So I can simply drag this into my buffer, and now it will be filled by the contents of this audio file. Okay. So there are a few ways of reading audio from a buffer. What I can do is to use the wave object, mc.wave. I believe if I go to the help file, this should be exactly what I need, right? And we can see the wave object, or wave tilde, needs one argument, and that is the name of the buffer from which it is going to read. In our case, it's read. We can also specify the start and end points. So let's say I want it to start from the 300th millisecond, and I want this to end at the 500 milliseconds. Or was it samples? Does it read from milliseconds or samples? Let's quickly check. The start point, it's a millisecond offset. So I'm starting from 300 milliseconds, and I read the wave until 500 milliseconds when this mc.wave receives a phasor ramp. So values going from 0 to 1. 0 is going to be 300 millisecond, 1 is going to be the 500 millisecond, and it's going to read through this buffer, making some nice sounds. All right, and to hear this, of course, I need to mix down the MC signal, so mc.mixdown 2, and of course the attribute autogain 1. And just so we have a regular audio signal and not an MC signal, I'm going to use mc.unpack 2. So this MC signal goes here. I have two audio signals here, and maybe later I can add some audio effects, like maybe we can add some reverb to hear something nice. But for now, I believe this should make at least some kind of sound. Yep, seems to work. It's very subtle. It's not very loud, but it seems to make some kind of sound, right? It's not very interesting. We can try to make it a bit more interesting later, but this is how we read through this information. Okay. So let's go back to actually using this data of the red channel into making something cool. So now I know the density of my matrix, right? I know how many red cells are present at each second, and I can use this information to generate a bunch of banks. So I can use, let's say, once again, metro, but I can leave the second inlet or the argument empty for now, and I can say whatever comes in, I want to receive that many banks per second. Right, so what I can do is, of course, this would not be the right value, but I can divide 1000, because metro's arguments are in milliseconds, by this value, and the resulting value when fed into metro as the time interval is going to give me this many banks per second. So to divide, so we have to do a reverse division, so exclamation mark, divide 1000 dot, because we might receive a floating point number. And if I do this, this is the amount of milliseconds. This is my time interval that I need to feed into metro. So I can simply put this here, and I can have my toggle, and then let's see if this sends out anything. Okay, so if I connect this to my click, for instance, let's see what happens. All right, and if I restart this, as you can see, the population does have an effect on what we are hearing. So we do have some very basic sonification right here. But there will be a problem, and that is if we reach 0 cells, which is a possibility. Sometimes it might blink out, sometimes we might have 0 cells. But if I give the argument 0, or if I send the value 0 to the second inlet of metro, it is not going to not send out banks. It's in fact going to send out banks as fast as it's humanly or computerly can. So I want to have a check for this, right? I want to make sure if I receive the value 0, metro does not send out a semi-infinite stream of banks. So let's use cell 0, right? If this value is 0. And I will say if cell receives 0, the resulting bank triggers the message 0, which will turn off this toggle, which means metro stops. The second outlet of cell, or the last outlet of cell, is the message if the input doesn't match. So if it's not 0, again, trigger the message 1, and then turn on my metro. As you can see, when this value is 0, the metro will be off, otherwise it's going to be on. So this is a nice quality check that we can use. Okay, now there is a little matter of something though. all these clicks are right now in order, right? So if I again do this, and if this thing decides to visualize itself, or maybe we can look at here, or I can just simply load the canvas again. As you can see, these are all in order, right? So starting from the beginning, and each new click is going through one of the possible 200 channels. But this results in some kind of a problem where I cannot really keep track of which cell I'm sonifying, right? I want to have it so I can say, if it's the 0th channel, or if it's the first channel, or if it's the 100 channel, then it's somewhere here, the particle or the cell that we are sonifying, so we can maybe read from a different position in the buffer. So I want to be able to keep track of where exactly the click is coming from. I want to inform the position of the click. And if that doesn't make a lot of sense because it's a bit of a complicated thing to wrap your head around, don't worry, we are going to fix this. So if I look at audio input, there is an attribute here that is not ticked. It's called per-chant triggers. I always read this as per-chant triggers for some reason, but it's per-chant triggers, per-channel triggers. And what this does is, and I can start the audio again, I can tick per-chant triggers or check it. And you will now notice when I send a click, it's always the very first instance of mc.snowphasor that receives, that creates the phasor. Right, because if per-chant triggers are checked, then it's going to expect then more MC click signals. So instead of a single audio signal going into mc.snowphasor, it's going to expect a multi-channel signal going in. And a click on one of those multi-channel channels is going to trigger a specific phasor here in my mc.snowphasor. So I can use this idea to trigger specific channels. So let's see how we can apply this. So chance 200, and I'm going to also enable per-chant triggers 1. Okay, and then I need an MC click, right? So mc.click, once again, I need to give it a chance attribute. So chance, again, 200. But how do I know which channel I'm going to trigger? And more importantly, how do I trigger an individual channel in mc.click? Okay, so let's use a bit of randomization for this, right? Because we know that on each instance, we are receiving a list of varying lengths that tells us the possible x and y coordinates. So maybe I can randomly choose one of these coordinates. I can somehow scale this, right, from 0 to 50 or 0 to 49, the range of my x coordinates to 0 to 200, or I think 1 to 200. I think multi-channel objects start counting from 1 because that's computer science for you. And I can somehow randomly trigger the somewhere on this x-axis. So let's see, let's use randomization. So I'm going to create a random object, right? And the length of this random object is going to be the length of this list, right? Because I want to be able to pick one of these elements. And if this list is 200 long or 10 long or 20 long, I want to know this and do something using it. So let's use zl_len, which is going to report us the length of the incoming lists. In this case, it's 8, and I can put this information into the second inlet of random, which is the random number range, right? So now let's say each metro gives us the result of this random generation. So this is the random index in the list of x coordinates I'm receiving. So I'm saying get the second one, get the first one, get the fifth one in this list, right? And doing this is also very easy. I can simply use zl_lookup, which is going to look up an incoming list based on the index number that I received. This can go into the second inlet of zl_lookup. So now my list containing the x coordinates is in the second inlet of zl_lookup, and then the value, so the index number, which I receive from random, goes into the first inlet of zl_lookup. And now I'm receiving my x values. So I'm just randomly picking x values from the pool of available coordinates, depending on wherever this game of life is at. Okay, so how do we click this? Let's look at the reference for MC objects, and I believe there was this, there we go, set value, direct a message to an individual channel. So maybe I can say something like set value and then the number of the channel, and then I can just simply type bank, right? So let's see, pack set value then the next value is going to be variable. So let's just type 0 for now, and then bank. So this should work, right? Now if I put the result of ZL_lookup into the second inlet, so I change this 0 value, I'm going to receive a bunch of messages that say set value something 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 bank. And ideally this is going to trigger something. But of course right now the results of the ZL_lookup is limited between 0 and 49 because these are the x coordinates of my jitter matrix. So I can improve on this by using scale, using the scale object, 0 to 49, and scale this to 1 to 200. Okay, so now I have a better spread of banks. And as you can see, the numbers are indeed working. So if I do this, I can already see it in this meter right here that it's lighting up only in specific places. It's not really scrolling down anymore. So the set value message is triggering clicks or impulses in certain multi-channels, which is because of the perchant triggers one attribute. mc.snowphasor is triggering very specific ramps. Okay, so far so good. So what else do we need to do? So what else do I want to do? So first of all, I want to think of the matter of clicks, right? And not the clicks I'm using here, but the audible clicks that does not really help with our experience of listening to music. And to showcase this, let's try starting over our game of life. And I don't know if the audio capture is capturing this, but I'm hearing some clicks in the middle, and that's because sometimes that there are these waves re-triggering, or at the end they're cut off abruptly, and there is not really an envelope following each particle, each phasor that is being sent here and is being used to read through this buffer by using MC wave. And let's turn this off because I said that's beginning to sound annoying when I'm trying to explain something. All right, so to fix this again, there is a new object that comes with the 8.3 update of Max that is called updown. Updown, which generates a trapezoidal function. I can use the MC version because I'm dealing with MC objects here. And if I look at the help, maybe I can easily read what it does. So an updown object is driven by a ramp from 0 to 1 or 1 to 0. Surprise, surprise, that's what we already have through mc.snowphasor. And it generates a trapezoidal function where the attack and release times are independent of the speed of the input ramp, unlike trapezoid where start and end times are specified as a proportion, yada yada yada. The point is this will generate an envelope. It's going to go from 0 to 1 using a very specific shape at the rate of the incoming phasor. So if there's a phasor here coming from 0 to 1, it is going to generate this envelope shape. There's values that go from 0 to 1 and then back to 0 at the end, exactly in that time of my snowphasor ramp. So if I can simply multiply the resulting envelope with the result of MC wave, so I'm very easily applying an envelope to the buffer playback, making sure I start with 0 and I end with 0 each time I'm playing back something from the buffer, meaning ideally no clicks. So mc.multiply tilde, and I'm multiplying this by whatever's coming out of mc.updown. And now this should sound slightly better. Of course, something I can do is give this an argument, so how long it takes for it to go up and down the ramp of the trapezoidal function. So let's give it 2020, for example. And if we look at the signals here, you can see it's generating these envelopes, right? They look a bit blocky in there, but don't worry, they are doing what they need to do. Okay, again, I'm going to delete this patch cord because now we are going to do one more thing to make this actually interesting, and that is to use these coordinates of the alive cells to choose different places to read from the buffer. Because you might have noticed the second and third inlets of mc.wave. The second inlet is the starting table location in milliseconds. So it essentially is this argument, right? The 300. So where do I start reading this buffer from? And the third inlet is the ending table location, as in which millisecond do I stop reading through this buffer. And because these are inlets, maybe I can change this by sending a multi-channel message. So each, let's say each multi-channel has a different starting position. right? Let me show you how. So let's say I have an mc.sig, right? This also has the chance 200 attributes. So now I am sending signals here. And right now these are all 0, right? mc.sig by default sends 0. So now I'm telling all instances of MC wave start reading from the very first or the 0th millisecond. But I can maybe use the spread message, right? Spread is, I guess, not an operator. It's a message in this case that we can send to a multi-channel object, especially multi-channel mc.sig, to generate a bunch of values that go from the first value I'm sending to the second value I'm sending. That did not make a lot of sense, did it? So let's say I write spread 100 to 1000. Right, let's say I send this message to mc.sig. Now, if I look here, you can see the very first channel is 100, and then it's increasing on each instance, right? So it's the first channel is 100, the 200th channel is 1000, and anything in between is anything in between. So I'm really sending different values to each instance of my MC wave because I'm generating multiple values using spread. So I can also use load bank to ensure that this message will load and this mc.sig is going to send this value when I restart this patch. And let's already see if this makes a difference, because I know MC click will trigger different channels of my mc.snowphasor depending on what's happening. So that might result in a different sound depending on where MC wave starts reading from based on which data, which signal mc.sig is sending to that specific channel. Okay, I am getting something different, so this does sound different. It doesn't sound perfect yet. And I can see a very obvious mistake here. So I start reading from a certain point, right? Either 100 or 1000 or something in between, but my endpoint is still fixed. It's 500, and I have not sent anything to the second inlet. So sometimes it's trying to read from 1000 to 500. Sometimes it's trying to read from 520 to 500. I guess trying to read something backwards, trying to read it in reverse. But we can also mess with this, right? So I can maybe, let's see, I can also create some kind of spread here, or maybe I can use the randomly chosen y value, randomly chosen coordinate here to load up a specific message. So let's say I create a mc.sig, right? Again, I have, actually I don't need to create an mc.sig. Okay, let's see. So what I'm going to do is whatever value is created here, I'm going to use mc.plus tilde operator to add 500 to this, or let's make it 200. Right, so now this is a signal that goes between 300 and 1200. So each time the length of the portion of the buffer I'm reading is fixed. We're getting a bunch of beatbox clicks now, which are the kind of clicks that we want. But then I can also mess with this value, right? So this is the fun of working with the MC objects, that if I'm adding something, maybe this can also vary depending on which y coordinate I'm reading from. So let's try to do something like this. I'm going to use another ZL lookup, and this is going to receive the y coordinates. Now this is also something I'm randomly choosing, right? So I can, for instance, use the same random value that I'm using for the x coordinate lookup, and I can send this to the y coordinate lookup. I can again scale this, and maybe this y coordinates can choose which signal here is going to, the value of the signal. Okay, let's do it like this. So I'm receiving now my y coordinates, right? And this is scaled to 1 to 200 because I have 200 channels. All right, so I again have to use the set value message that I have been using here, but this time I need to trigger a few pieces of more information, right? So I need to say set value. I need to say the value I am setting. Notice the channel number of the value I'm setting. So let's say I'm setting the value of the 20th channel of this mc.sig to 440 no, 4,400, for example. So now that specific channel will add that much to this incoming spread mc.sig. And I want this to be based on the y coordinates. So how do I do this? So instead of pack, I'm going to use pack, the classical pack, right? And I'm going to say I need, again, set value. I need my coordinate, and then I need my value that I'm sending. And I need this to happen at a specific rate. So what I can do is I can use trigger, right? Again, I'm receiving this value, but first I want to trigger the integer number, then I want to trigger it again. And then last, I want to send out a bang. But of course, a bang then should be on the leftmost side of my arguments, because this trigger is going to go from right to left. So first, I have my integer. I'm going to multiply this by, let's say, 5, right? Multiply this by 5. So let's say if it's 200, the incoming value is 200, it's even larger. So this offset I'm adding to via this MC plus object is going to be even larger. And then with the second integer number, or the same integer number being sent twice, I'm setting the channel that is going to be affected by this value. And then last but not least, I'm sending out my bang. And doing this should have a specific amount of offsets for each MC signal. And this is different than the spread, right? You might be wondering, why am I not using spread also here to have this two-dimensional space in which I'm reading the buffer using wave, which is also fine, but this is another way of working. This is really using the coordinates of the matrices to drive very specific data into MC. So it's also important to be aware of this way of working using these objects. And let's see how this sounds. So I'm going to do this. And there we go, we are hearing the individual cells. Now, something I can do is, instead of multiplying this by 5, maybe I can again use a scale operator to get a fancier range. So let's see, I'm using scale. That goes from 1 to 200. That's my input range of values. And I want this to be between, let's say, 100 to 750. I'm just completely being random with this right now. So this should result in a slightly different kind of sound. So now we have more sounds on the low end. So if the value is higher, then of course we are reading through the buffer at a different rate. And if this is lower, we are reading through the buffer at a different rate. So the point is, the scale being different affects the speed in which this is read. And this is really cool. You can see when the game of life settles down, you're just getting these few sounds, these last pieces being sonified. So we're getting this beatbox game of life. And to stop this from working, I can simply turn off this metro that is sending out the jitter matrices, and I can, I guess, delete this patch cord again. Later I can add a system that actually maybe uses a gate to send this message, so the clicks are not being used if I want to turn this whole system off. And lastly, maybe I can add a bit of reverb to make this cool. Now for this, I'm going to use the Valhalla Supermassive VST that you can download for free. This video is not being sponsored by Valhalla, but they have a very neat reverb. So if I use this VST object, maybe I can get a nicer kind of sound. But I can turn on this, I can change my preset to Triangulum Hall. There we go. Now it sounds like a gigantic hall. Someone's beatboxing in the cathedral. Then I can turn the mix down so the sound is not so wet. And there we go, we have soundified the game of life, or, well, more specifically, we have soundified a part of Game of Life. As you can see, there is still the green channel, there is still the blue channel, so that is something maybe for you to experiment. Can you add the same algorithm in these other channels? Can you tweak this algorithm to maybe read through wave in a different way, or you use something completely different. Instead of wave, maybe this is processing a filter or a phasor effect, or it's doing or it's messing with the values of this reverb. Once you have this data, you can essentially do whatever you want with the sound. That's the fun with sonification. It's also up to you to find interesting applications of this data to sonify visual ideas, such as a game of life here. So I hope you have fun with it. I hope you tweak this. I hope you come up with cool things. And once again, thank you for watching.